Welcome to today's webinar brought to you by Bruker Optics and Gamry Instruments, entitled Spectroelectrochemistry, More Than Just the Sum of Its Parts. We have two speakers today. Our first speaker is Sergey Shilov. Sergey Shilov is the R&D manager for North America at Bruker Optics. Sergey joined Bruker in 2001. He is responsible for the support and development of new applications for the Bruker Research FTIR systems. He received his PhD in 1992 from the Russian Academy of Sciences in polymer physics and his master's degree from St. Petersburg State University in Russia in physics in 1986. The Alexander von Humboldt Foundation in Germany awarded him research fellowship in 1996. Sergey published 37 papers in peer-reviewed journals. His research interests include time-resolved FTIR spectroscopy, surface science, polymer, and life science applications. Our second speaker is Dave Loveday. Dave Loveday grew up in Kent, near London, in the United Kingdom, and received his PhD in chemistry from the University of Bristol. He also earned both his bachelor's and master's degrees at Bristol. Dave's research advisor was Dr. Rob Hillman. Dave's research used electrochemical techniques with a quartz crystal microbalance to study polymer films. He even employed EIS to characterize the films. Dave came to the US for a postdoctoral appointment at the University of Texas at Dallas. He served as the electrochemist supreme in Dr. John Ferraris's lab, in which the primary research effort was directed at conductive polymers. Since Dave joined Gamry in 2001, he's enthusiastically made the transition from research laboratory to commercial enterprise. If you have any questions during the presentation, please submit them via the questions drop-down box located to the right of your screen. We will take some time at the end of the presentation to answer your questions. Now we will begin today's presentation.
Okay. Do you see my screen, Julie?
Yes, I can see it.
Okay. Well, let's thank you for introductions, and we start spectroelectrochemistry, more than just the sum of its parts presentations. In the first few slides, I would like you to show how in principle of FTIR spectroscopy. So you know that all molecules vibrate, and if molecule has a dipole moment, and dipole moment changes during vibration, molecule will behave as a small antenna. It will absorb light on the frequency of vibration. We know from the basic physics that a molecule vibrates at a frequency of 4,200 wave numbers. That is actually mid-infrared spectrum range. If we take a look on the spectrum of a molecule shown on these slides, you will see a few bands, and each individual band can be assigned to a specific vibration inside the molecule. Like example of a CH stretching vibration, carbonyl stretching vibration, CS to scissoring vibration, or skeleton vibration of big molecules. The beauty of infrared spectroscopy, that's if you have a spectrum, you can get some information about the chemical structure of the molecule. So how we can link electrochemistry in infrared spectroscopy? Electrochemistry, as you know, studies the relationships between electricity and chemical change. IR spectroscopy gives you characteristics of a spectrum for each substance except for homonuclear diatomic gases and pure metals. So means if we combine these two techniques, infrared spectrochemistry will offer insight interaction mechanism and may permit the study of intermediate and short-lived species. So that technique can be applied for investigation of both electrolyte, solutes, electrode surfaces, and can be used on different electrochemical studies like electrochemical reversible reactions, oxidation processes, electrosynthesis reaction of biomolecules, and many other techniques. What are the main components of the setups if you would like to perform this experiment? You need to have a spectrometer with a liquid nitrogen cool detector, give you high sensitivity. You need to have an accessory which is allow you to use your spectroelectrochemical cell inside the FTIR spectrometer. Of course, you need electrochemical cell, also potentiostats. This slide shows the basic components of electrochemical setup, which does include cell and potentiostat. And you need to have a FTIR spectrometer. Bruker has different flavors of spectrometers from Linear R and X, the use of our purge gas, and the Vertex 70 ATV for its vacuum spectrometer. As I mentioned, you need to have liquid nitrogen cool detector, and you will have an adaptation which adapt your electrochemical cell to this spectrometer. And we will discuss this adaptation design on the next slides. So first of all, this is about spectrometer. Which spectrometer will be good for such research? So that depends on the spectral range you're interested in. So it depends on the spectrometer. It can be operate from UV to far infrared. Also scan speed. So how fast you can to acquire spectra. So it depends on the spectrometer model. You can do 50 spectra per second or 87 spectra per second. Now let's talk about how we can combine your electrochemical cell with FTIR. So we have a special design for accessory which is allowed to produce your electrochemical cells experiment. So this design of this accessory shown on these slides. It has two mirror sets with 30 degrees and 60 degrees incidence angle and can be adjustable angle plus minus 5 degrees. We have a holder for polarizer, intake for electrochemical cell, and this accessory allows different type of experiments for electrochemical measurements. Let's take a look on a closer on the design of this accessory. So it's, as I mentioned, we have two mirrors, which just allow light to couple inside the electrochemical cell. It's have a hemispherical window, just couple light to the cell. Light from spectrometer goes reflected from the mirrors and goes to these windows and then introduced to the cell. And also, it's allowed to mount polarizer. Polarizer is one of the essential part of these setups if you would like to study surface chemistry. Let's take a look on a closer what kind of experiments you can do with such design. There's basically 3 experiments you can perform. Experiment number 1 is thin layer configuration. So where you investigate electrode surface and electrolyte. You can see design of this cells. So you have a reference electrodes above of this coupling hemisphere. So typically, it's this slide exaggerates this how above it is, but typically it's pressed against the window. And in this setup, we use external reflection setup with a barium fluoride, calcium fluoride, or zinc selenide window. So as you can see here, light from spectrometer goes through the hemisphere and then goes through electrolyte, reflecting from the surface of working electrode, goes from electrolyte again, and then goes to the detector. As you can see, most of the signal comes from electrolyte, and a part of it is also from the surface, but mostly from electrolyte. So now to describe another 2 types of experiments that you can perform with this accessory, we need to talk about, first of all, about attenuated total reflectors. So how this ATR works. So assume you have a hemisphere and you introduce light to this hemisphere. And at the point where the light touching the surface of hemisphere, it creates so-called evanescent wave or freestanding wave. And if you have a sample on the top of this hemisphere, and if sample absorbed infrared radiation, you get a spectrum. So this is the typical applications design of ATR spectroscopy. How far light will penetrate inside sample depends on many factors, and it depends on the wavelength of light, refractive index of sample, refractive index of a crystal, or also the incidence end. So now let's take a look and use this design for electrochemical studies. So you can see how does it work. We use an internal hemisphere made of silicon, germanium, and zinc selenide. We shine infrared light, and it will create evanescent wave. And in these configurations, working electrode is above the surface of the crystal, and standing only penetrates to electrolyte. So for this setup, we measure only what's going on during electrochemical reactions and what's going on only inside electrolytes. We are not talking about surface chemistry on the working electrodes. So, but we also can do another experiment. If we cover the top of our ATR crystal with thin layer of metal, thin means typically about 30 nanometers. It's a semi-transparent for infrared light. So it's, as you see here, it's a evanescent wave will be also created in this setup. But we use this layer as a working electrodes. As a result, we only see mostly see, I would say, what's going on the surface of an electrode during these electrochemical setups. So as you see, there is 3 basic experiments you can do, 2 experiments with ATR and 1 experiment in reflection. So next important question is how you can introduce your electrochemical cell for such measurements. So we do not offer, as a Bruker, as a company, we do not offer cell itself, because it may be just specific for each experiment. But what we can do, so we offer a glass body for which is you can introduce your cell inside. And if you're interested, we also can provide you a file which is you can print an electrochemical cell using 3D printer. This file and this setup shown on the right side and developed by one of our customers. This is another solution for custom-made spectroelectrochemical cells shown here, and it's published in Electrochemicals Actor, so you can see here. And if you would like to have more details, you can see the reference in the bottom. And another very interesting setup was offered recently by a German scientist. We use a setup with micrometer screw and special electrodes, which is allow precisely control the distance between working electrodes and ATR crystal or reflecting crystal used for the reflectance. That's very important for this experiment to know what's this exact distance between electrodes and the crystal surface. And if you would like to get more information, take a look on this paper. So for those who would like to have a complete setup, say not interested to make own electrochemical cells, so Pipe Technology offer a jackfish electrochemical cell, which is developed by a company in Canada, is headed by Jan Burgess. So actually supply me a couple slides for these presentations. You can see here, this shows a pipe ATR, VMAX ATR, and a jackfish cell mounted on the top. So that's an important thing. So also when you apply a thin electrochemical layer on the top of electrodes, depends on the thickness and also depends on what kind of metals layer you use, and also can create enhancement of the signal. So this enhancement called ATR, surface enhancement infrared absorption spectroscopy. So enhancement of the signal tremendously helps to see what's going on exactly on the surface of the electrodes. So that's a technique is very well developed. So the key point is to make very good layer, coating layer, metal layer on FTIR electrodes. So, and all this technique described in the publications shown here. And thank you, Jan Borges, for providing me this slide. And other things, when you do this type of experiments, how you can combine with potentiostats, how technically you can connect it. So technically it's pretty easy. So instrument, FTIR instrument supplies a trigger signal, so we can use up to 4 different trigger signals. And also, if your potentiostat have a trigger capability, so potentiostat can supply trigger signal to start FTIR spectrometer to start data acquisition or to change potential and so on. So there is a different option for doing this. Another features of this device, then we also can record simultaneously up to 2 user signals. For example, you can record pressure, temperature of electrolyte, or you can also record the potential simultaneously with the measurements. So now I switch to a few examples of such applications. And the first one will be oxidation of metal organic complexes of ferrocyanide. We use a FTIR spectrometry and we use a FTIR mode or reflections. FTIR spectra are recorded at constant potential applied to every potential level. And to guarantee chemical reversibility of the reaction, the potential is set back to the reference potential after each step. So that shows you example on the right, shows you how we change potential and record signal at each step. So how we did this, we actually collected spectra different potential, use so-called time resolved spectroscopy. But in this case, we have not used time resolution. We just change potential, record spectrum, and plot spectrum versus applied potential. So a typical presentation is we subtract the spectrum at 0 potential and get spectrum like this. So if you see there's a few positive bands and some on negative bands. So negative bands means that material is consumed during the reaction. So, and positive bands means their intensity increase, means that the amount of this material is up during the reaction. As you can see, it's pretty clear. So that's which compounds go down and which compound is going up during this type of reaction. Another example of oxidation of alcohols using platinum electrodes. That's what we did here. We use the reflection measurements at the surface using platinum working electrodes in thin electrolyte layer configurations. Other measurement conditions, we use a calcium fluoride hemisphere, so 60 degrees angle of incidence. We use polarization light to discriminate between electrode surface and electrolyte. And you can see here that's what we expecting to see, different combinations of CO triple bonds. And then actually what happens that you can see here against this we use the representations subtract the potential at 0 potential. You see bands which is go down means that bands are consumed. So that's, as you see, we can technically see what's exactly going on in terms of chemistry when you do this type of studies. That's on the bottom showing you the typical measurements, how typical setups with vortex, vacuum vortex spectrometer, electrochemical cells inside here, and more details in that publication. And another application example will be electrooxidation of glycerol. So what we did here, we did reflection measurements on the electrodes surface of a platinum working electrodes through a very thin electrolyte layer. different cell potentials and the switch potential from 0.05 volts to 1.3 volts, and see what's going on, what kind of reaction mechanism was going on during this reaction. As you can see here, we can obtain spectra at different potentials, subtract spectrum at 0 potential, and see all the bands. That's pretty wide bands, consists of many smaller bands, and we can assign all individual bands. If we can make a deconvolution, spectrum deconvolution, and see assign different bands to different molecular structures, and you can see on the bottom what kind of reference values we can use for different assignment. And the last slide about interesting applications for electrochemistry is studying orientation of molecules on the surface of electrode. So the beauty of infrared spectroscopy is also that you can see not only chemical composition, but you also allow to see the structure. If your structure formed on electrodes is well organized, like on these molecules phospholipid bilayer, the bands becomes very more narrow, and you can judge whether you have a random orientation or you can have a more organized layer. So based just on the width of these bands and also on the position of this. From that, you also calculate the tilt of these molecules to the surface layer normal. And you can see from these publications, when you do this electrochemical studies, you can actually see that the tilt of molecules attached to the surface is changing during the changes of potential. So it's very interesting research for such applications. So as you can see, spectroelectrochemistry gives you insight, not just only what's going on chemically during the electrochemical reaction, but you also can learn more about how organized the layer, or what the tilt angle, and many other applications can be used from these studies. With this, I would like to finish and pass the presentation to the next colleague from Gamry.
Thanks, Sergey, for a really interesting talk. I think some of the... can you see my screen?
Yes.
So I think some of the things that you mentioned maybe overlap with what I'm going to say, but that's fine. And I wanted to give a short introduction to electrochemistry and potentiostats, and give you a little bit of information at the end about spectral electrochemical measurements and combining the potentiostat with your spectrometer. Already Sergey alluded to a little bit of that anyway, so I think I'll just maybe elaborate a little bit. So a little problem changing slides there. Electrochemistry is the study of electron transfer reactions where chemical change involves the exchange or movement of electrons. Generically speaking, it's shown as an equation where an oxidized species gains electrons to become reduced, and the definition, oxidation is a loss of electrons, and reduction is the gain of electrons. So here's a cartoon of electrode in contact with a solution, showing in this case an iron surface which has the oxidation of iron to iron to ions that go into solution, and then the movement of the electrons in the electrode. And here we have a stylized model of the electrode electrolyte interface indicating the layers close to the electrode surface. The closest layer is called the inner Helmholtz plane, where you see solvent and any adsorbed ions reside, and then slightly further out is the outer Helmholtz plane, where solvated ions in solution are, and you can see that the surface of the electrode attracts ions from solution of the opposite charge. So in electrochemistry, everything of interest takes place at the interface. So now that we've had a quick look at the electrode, how can we study it? And for this, we're going to need to use a device called a potentiostat. So what is a potentiostat? It's an electronic instrument that measures and controls the voltage difference between a working electrode and a reference electrode. And it also measures the current flow that flows between the working electrode and the counter electrode. And the controlling the potential allows us to control the thermodynamic state of the electrode or sample. A potentiostat can also be a galvanostat. So as well as controlling the potential, most potentiostats can operate as a galvanostat as well. So in this case, rather than controlling the potential, we're going to control the current between the working electrode and the counter electrode. In general, the potential is also measured. However, in current controlled experiments, interpretation is a little bit more complicated because we don't exactly know where the current, which reactions the current goes to satisfy. So I'm just showing you a couple of pictures here of a couple of Gamry potentiostats. On the left is the reference 600 plus, which is a high performance potentiostat, can measure very low currents. So for very small electrodes, if we've got very small amounts or small amounts of material. And it's, and when I'm talking about low currents, I'm talking about going into the picoamp range. And on the right is the interface 1010, which is a more general purpose research grade potentiostat, but it can also still measure pretty low currents down into the nanoamp range. So the potentiostat's used to control the electrode by raising or lowering the energy of the electrons in the electrode. It sits so that the potential sits at, so it sets the potential so that electron transfer can go downhill. So in the case of reduction, we need to raise the energy of the electron so that they can pass to the molecule in solution. And in the case of oxidation, we need to lower the energy of the electrons so that electrons can be transferred into the electrode. And you can also think of the electrode potential in terms of the thermodynamic state, like delta G. So the potentiostat works with 3 electrodes, usually immersed in some conductive electrolyte. The working electrode or sample electrode is the place where the reactions of interest take place, either close to the electrode in solution or from the electrode itself. The reference electrode is the electrode with the constant electrochemical potential, where we reference all the potentials that we measure against the reference electrode. And the counter electrode is an inert current carrying electrode that completes the cell circuit. So why does the potentiostat have 3 electrodes? And the reason for that is we'd like to study the electrochemical reactions or events that take place at one specific electrode, the working or sample electrode, So the use of the 3-electrode potentiostat allows us to separate the reference and counter electrode. So the current flows between the working electrode and the counter electrode, and the potential is measured between the working electrode and the reference electrode, with and no current flows down in the working electrode reference electrode circuit, or very little current, and so there's little or no interference from the other electrodes. So as you saw from Sergey's presentation, there are spectroelectrochemical experiments require specialized cells, and usually those would be provided. They're often provided by the end user. But I'd like to show just a standard electrochemical cell for explanatory purposes. So it's usually made up of some kind of borosilicate glass vessel that can hold a solution and has ports in it that allow electrodes and gases to be introduced. In addition, the cell may have some kind of temperature control, given that we're measuring thermodynamic and kinetic quantities, which are susceptible to thermal changes. So the working electrode or sample electrode is either an inert metal where the electroactive compounds are going to be reacted, or it's a material that has properties of interest. Common inert electrodes are platinum, gold, or glassy carbon, and may come in electrodes like the ones shown, where you have a polished disc that's exposed to the solution. The counter electrode also needs to be of an inert material, where reactions are facile. Platinum is a common material, like the wire that's shown. You may also want to have a larger surface area electrode, so sometimes a platinum gauze is used, and platinum is easy to use because it's easy to clean. During the reactions, an equal and opposite current flows at the counter electrode as at the working electrode, so it needs to be able to support those reactions without changing the potential too much. Reference electrode is used because what the potentials that we measure on a relative scale, so the reference electrode has to have a stable, constant electrochemical potential, and so it uses electrochemical couple that has a stable potential. Common aqueous reference electrodes are like the one shown, the saturated calomel reference electrode, but also could be something like a silver-silver chloride reference electrode. So in the electrochemical cell, the actual cell becomes part of the potentiostat circuit, and hence its properties affect the performance of the potentiostat. In particular, the reference electrode is in the feedback circuit to control the potential. So often special attention needs to be given to the reference electrode, as in the case of a potentiostat, it needs to have a low resistance or low impedance, as it's called. So that can be achieved having a large junction at the tip of the reference electrode, using highly porous glass frits. These can sometimes, because they have very fine capillaries, they can be blocked, and so regular replacement of these isolation frits can help to improve the impedance measurement of the electrode. Potentiostats are much less forgiving for the high impedance reference electrodes that you can buy than the ones used for pH meters. And so the reason is because to control the potential, we need to have a fast moving circuit that can adjust the potential in very small increments. And often when you find there's a problem in your with the working of your potentiostat, and it's in the cell, it's often due to the reference electrode. So the common electrochemical experiments of interest for spectroelectrochemistry, although there's not exhaustive list, something like either, as Sergey showed, a constant potential amperometry, where you hold a constant state, or potential steps, where you step the potential to different levels, called chronoamperometry, and also cyclic voltammetry, where the potential is cycled between several limits at a constant rate or scan rate. Linear sweep voltammetry, which is a subset of cyclic voltammetry, may also be of interest. So in a constant potential or chronoamperometry type experiment, we might start at one potential level, step the potential to another for a certain length of time, and then step the potential back to the original potential, or maybe another potential. And the resulting current is shown on the right here, where you get a current spike that decays to a steady state. And then when we step back, we re-oxidize or re-reduce whatever was oxidized in the first place, and we get another current spike that goes to a steady state. In the case of cyclic voltammetry, on the right we show the ramp where we're changing the potential of the electrode at a constant rate to a particular limit, and then reversing that, and the resulting current gives you this classic what's called a duck shape cyclic voltammogram for a reversible electrochemical couple. So in a specific spectroelectrochemical setup, we want to, in general, the control of both instruments is not integrated into one application. Each instrument uses its own data acquisition program. So how do they communicate? In general, you'd like to synchronize in some way the two instruments so that you can match up the voltage time profiles with the spectra that you take. Since both instruments are going to be operated in their own programming environment, we have to have some way to allow to get the two instruments to start at about the same time, and that can be done, as Sergey mentioned, by some kind of, in the Gamry case, we have a special triggering cable that connect the two instruments. So this is a picture of the cable. Basically, at one end it connects to the potentiostat, and at the other end it has some leads that can be connected either directly to the other instrument, or to other connectors that fit on that instrument. And here's the connector that's shown on the back of a reference 600 or reference 600 plus instrument, where you will put that cable to send out or receive triggers, so that you can synchronize the measurements. So I want to thank you for listening to the presentation, and I think I'll hand it back to Julie.
That's all the time we have today. If we're not able to answer your question here, we'll answer it directly to you by email. You can either submit your question directly to Sergey Shilov at sergey.shilov@bruker.com, or Dave Loveday at dloveday@gamry.com. This recording will also be posted in both the Bruker and Gamry websites for future viewing. Thank you very much for joining us today.
Thank you.